I don't know if you looked online, but here's it back. All right, hello class. Yeah. Oh, you're just waving. All right, thank you. Thank you. See, as far as the camera knows, you're all waving at me, but yeah. Even though, no, they're all sitting there. All right. You guys have any questions about anything? Because I know you're all, looking at the homework and studying and getting ahead. And I'll give you the opportunity. Anybody after class, I'm just curious, did you notice anything about color since last lecture? Did anybody look at anything and go, oh, and at least start thinking about the lecture and why it's, all right, we got one. Okay. Well, color will come up some more when we get talk about some of the other things that can happen with light waves. All right, so we did color mixing. What are the additive primary colors? Red, green, and blue. It's those three that our eyes are responsive to, and it determines what colors we think we see. So if you just add those together with light, you can get any other color. A lot of it, we deal more with pigments and inks and crayons and filtering, and we subtract out some of those red, green, and blue, leaving the others. And so to make life easier, we call those subtractive primaries that we deal with what? What are those colors? Cyan, magenta, and yellow. Right. Those are the subtractive primaries. I like to call them the secondaries because they're not as important. But they filter out and subtract red, green, or blue, leaving the leftovers to see. And that's the color we think we see. All right, we got to why the sky was blue. Do you remember why? Scattering. That's the term I was hoping for. Yeah. Blue light gets scattered more. It's off the oxygen and nitrogen molecules. Those are really, really, really small compared to the size of a blue wavelength. And so they get scattered more than red light, because red has a longer wave. Think of it, you got this big wave, we'll exaggerate, and that runs into a little particle like this. It doesn't get as affected as much by this particle as a little wave. He'll get affected more. Does that make sense? So that's the idea between red light and blue light. All colors get affected. Red light is still scattered, but blue light gets scattered more. And scattering is a little different than reflecting. Reflecting, remember you absorb the light, some of the materials, causes them to vibrate. They re-emit light as the same frequency back. Scattering is more like it just kind of goes a different direction, emitted in all directions. Because, reflection, it's like what you see in a mirror. You have to look at certain angles to see specific things. Scattering, when it hits it, it'll scatter in all directions. That's why the sky looks blue in every direction.
As the photon of light gets into the atom of oxygen or nitrogen, it disrupts the electron valence shell?
It does interact. The incoming light does interact with the electrons in it, but it causes them to scatter in all directions.
That's why it scatters.
Yeah, you can think of it more as a collision, like with billiard balls in that sense. So the wave comes in. If it hits a little dinky thing, something that's small, it might come off, and to simplify, it can scatter that way, this way, this way, this way, this way, this way, this way, in all directions. Where reflection is more like, we're going to cover that more today, it'll bounce back at a certain angle. Not in all directions. That's reflection, this is scattering, and that's what the sky's doing to blue light more than any other. I thought of another way to do this. See how well this works. I thought it worked great yesterday. Let's see. Let's do this one. So here's 3 different colored lasers. And here's water with some coffee mate in it. Little particles in it to help scatter the light. Another thing to note is you don't see the laser beam, do you? You can see where it reflects off the table, but you don't see it through here like you do in Hollywood. Yeah, you don't, unless the beam has something to scatter off of, like that. Can you see the beam now? It's scattering. Red gets scattered, and you can kind of gauge that by how far, or how deep it goes through. You can see it gets dimmer as it goes down. Well, green light gets scattered also. And it's a little harder to tell because our eyes are more responsive to green. So green looks brighter to us. These are all the same intensity. Remember with sound, intensity is objective. They all have the same intensity, same power per square area. Per square area, that was redundant. Per square, over the same area. But green looks brighter to me than red. But what you can notice is, hopefully, the red doesn't seem to scatter as much up here as the green does. This water looks more green to me than red, so more green is being scattered. Can you see that? Give me some response. Is it better darker maybe? We'll give it a go. And here is blue, which you might not be able to see at all. Let me turn the others off. You can see there's kind of a violet-blue glow. It's getting scattered, but do you see the beam go down? No, it's a shorter wavelength that's getting scattered more than the green. But the green's getting scattered a little more than the red. And that's what's happening in our atmosphere. And the more atmosphere it goes through, like when the sun gets lower and it has to go through more of our atmosphere to get to our eyes, then not only is the violet scattered out, but more green scattered out. And you're left with the longer wavelengths, like red. And that's why sunsets look more red. Why the lights are off. I'll do this one again. It was that piece of slag glass or something. You can see on your left, it looks blue. You see the scattered blue light. But by the time it gets to the right, it's yellower. And it's scattered too, but it goes further through our atmosphere because it has longer wavelengths. And the flashlight actually looks kind of red-orange, hopefully, to you. If I do this, can everybody see it? At least in one turn or another. Okay. So, that one. Scattering. Selective scattering. So the sunset is through selective transmission. It's the ones that get through. Why are clouds white? Say that again? Refracts the light back. Water droplets do refract light. That is true. But that is not why clouds look white. It's why rainbows give us color. And we're going to do that too. But let's think this through. You can reason things now, color. If clouds are white, what colors are coming to our eye? Yeah, red, green, and blue, all wavelengths. What's the cloud made up of? Water droplets, yeah. Take a clue from the sky. If little things like oxygen and nitrogen scatter wavelengths, so can water droplets. They're a lot bigger than oxygen and nitrogen, but they're still really small compared to the wavelengths of visible light. And the really small ones, you could think of, say you have some itty-bitty guys. Then that will scatter the blue light. If you have bigger ones, maybe, I don't know, more on the size of red's wavelength, they'll get scattered more. And of course, you can have intermediate ones, which can scatter the green more. All three must be getting scattered. You know this because all three are coming to our eye to make white. So a cloud is made up of different sized water droplets, like mayonnaise. What else is white? Milk. This kind of looks white. It has particles in there that are scattering all colors. You saw it when I shone the light through. It's a good scatterer. Wax is another good thing. Here's some paraffin wax. If I turn on this light bulb, make it a little dimmer. Can you see that the left side's brighter? And it looks white. There's different sized particles in there scattering the three different wavelengths. That's why clouds look white. They're made up of a variety of sized water droplets. So why do you think this one's dark? Well, this cloud, so to speak, is blocking this cloud, isn't it? I actually cheated. This is there's a piece of aluminum foil in between the two. Watch this. Ready? But some clouds look dark, don't they? Well, they're just in the shadow of another cloud. Or the sunlight's trying to come through it as opposed to reflect off of it. Some clouds, though, I mean, what's gray? What colors make up gray? Cyan, magenta, yellow? Nope. What makes white? Very good. Red, green, and blue make white. Red, green, and blue make gray, just less intense. There's not as much red and green and blue, but all three of them are there, so it looks gray. So they must be getting absorbed more by even bigger water molecules. The thunder clouds have a whole lot of water droplets, and even bigger because they've accumulated. It's so much they get so heavy it falls out. You get raindrops. You can, yeah. I would see green clouds. The sky would be this dark, ominous green. And I worried because that's when I figured a tornado was coming. I remember one day I looked up and it was like you could draw a line, a sharp line down the sky. And this side, light blue, scattering, fluffy white clouds all the way to the horizon, birds chirping. And this side, all the way to the horizon, completely solid, ominous, dark green. And sure enough, tornadoes came. But yeah, and it had to do with the water droplets scattering, absorbing. But yeah, gray is still red, green, and blue, just less intense, but all three. Kind of like yellow is red and green, but if you dim those, they look orange or brown. But yeah, mayonnaise, milk, I can't think of others at the moment, but that's why they're white. That's not the right button. There we go. Water. You ever wonder why lakes, oceans, look kind of green or blue? What's going on there? Well, let's see, if they're green and blue, what color is getting absorbed and not coming back out of it? Red. Water molecules resonate in the infrared, longer waves. So the red visible spectrum resonates a little more than the blue side. Red gets absorbed because it causes the water molecules to start vibrating a lot. It really likes microwaves too. That's why they start moving around. Well, if your water absorbs the red, then the blue and the green is what comes back out. Yeah, the deeper you get, the more gets absorbed. Absolutely. Any of you scuba dive? Or you've seen pictures of things underneath? If you don't use a flash, there's no red light down there. So things look kind of blue and boring and blah. So because there's no red light to reflect off the fish. So if the fish is yellow, you won't see that red light because there was nothing to reflect in the first place. It'll look dark or brown or gray or blue. Oh, that was my other example. Misters, ultrasonic humidifiers, or steam. a bunch of little water vapor droplets. That's how you can see it, because it's scattering the three colors, and it looks white. Even the sky, towards the sun more, the three wavelengths get scattered, and it looks whiter, less blue. Ice. If you can get ice to freeze nice and clear, but what if you crush it up? You create a bunch of little pockets in different sized particles, and it looks more opaque, white. Just another example. And here's one. How many of you have brown eyes? You are absorbing which color? It's a little harder, but I did just say this color combo. Say again? Blue and green. Yellow is red and green. Orange was red and green, but less. Brown was even less. So it's absorbing a lot, but it's definitely absorbing blue the most. And so there's that little bit of red and green to come back, and you look brown. Interesting, though, how many of you are blue-eyed? Me too. That's scattering. It's not due to a pigment. It's not absorbing colors. It's scattering the short wavelength blue because of particles in your iris, like the sky. You blue-eyed people can say that. Green's kind of a combination in between the two. I still don't fully understand it. But you have some pigment like brown-eyed, but there's some scattering also. And then different combinations for hazel and gray and albinos. And all right, clicker time. Session ID's up there. Give you a minute to log in. And I picked 4 questions. See if you're getting this color stuff. Anybody still need the session ID number? Holler. All right, number 16, we'll start with that one. Polling is open, go. So we're mixing magenta and yellow ink. So what color do you see? If you forget what magenta was, ask your neighbor. I'm 44 usually, isn't it? Oh. Helps if I plug in the receiver, doesn't it? Sorry about that. I'm a dork. Okay, there we go. Is it working? That would be why people were taking longer. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Meh. 67% say red. Very good. Magenta is red and blue. So that dot is absorbing green. Yellow dots absorb blue. So the only one that doesn't get absorbed is red. It reflects back at you. All right, go. What do we call this method of mixing? Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1. 55% got it right. Color subtraction. The inks are subtracting colors. They're filtering, absorbing. That's color subtraction. Addition is adding light together, shining light. Interference is like sound. They're canceling each other out. We haven't discussed that yet with light. Scattering, we just discussed, like with the eyeball, blue eyes, or the sky. The blue just gets scattered out. Inks are subtractive. All right? Go. See if you remember this one. I like how the author too chose sun up instead of sunrise, but whatever. Why is that sun red? Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1. Good. That's what I figured. We're split between absorbed and scattered. Okay, before I give you the answer, what gets scattered? Blue. So that's why the sky is blue. Selective scattering. But the sun is red because something got through. It was not scattered, and it was not absorbed. It was That's not right.
That is not right.
This author's wrong. It's selective transmission. That's wrong. I didn't catch that. The sky is blue through selective scattering because it scatters the blue. The sun gets through and is transmitted. That's why it looks that way. Oh, the redness of a sun-up or sunset is due mostly to light that hasn't been scattered. Well, there's 2 for 2 today. 0 for 2. Yeah, it's Friday. You understand my point? I misread the question myself. Light that hasn't been scattered. Right. The blue gets scattered. So the correct answer to this is scattered. The author, sorry, Hewitt, you are correct. Blue gets scattered. That's really what I want you to know. And red gets transmitted. Whether you understand the question or not. That makes sense? I'm sorry.
Another way we can look at it is, so blue scatters, and then the red, when it comes in, there's less blue, so there's less scattering. Less is scattering.
Correct.
When the sun goes down, less is scattering. There's more red getting through.
Correct. Blue is scattered, red scattered, but less. So it transmits through. One more. Let's see if I can blow it too. All right, one more here. I wanted to do this one. If molecules in the sky scattered low frequency light more than high, the color of the sky at noon would be, basically we're pretending the sky was a little different. 10, 9, 8, 7, 6, 5, 4, 3, excuse me, 2, 1. 61% red, very good. Right now, it selectively scatters the blue, the high frequency. This is just swapped. So what color would the sunset appear in this sky? Blue, right. Very good. All right. You can put your clickers away.
Does that ever happen?
Maybe some other planet. Might happen. Might be a different atmosphere that scatters things differently. Different thickness. Okay, chapter 28. I'll start. Reflection. Chapter 28 is, 26 was properties of light, how they're electromagnetic, and how they absorb and take longer to go through something. We just did color, so how we perceive it and how our eyes work a little. 28 is reflection and refraction, how it behaves. And this is very similar to sound waves. They reflect and refract also. Same rules apply. So I'm hoping a lot of this is review. But we can apply it specifically to light things. But everything I say still applies to the sound, any type of wave. So, if you have point A and point B, and you want to get from point A to point B, with light, a lot of people want to use what's called Fermat Principal. It's basically just a principle of least time. You can think of light rays want to get from A to B in the least amount of time. So they take the path to make that so. And so that would be straight. We know that. But if you have a mirror here, what's the fastest way to get from A to B off the mirror? Well, you could go straight down and then over. Or maybe you go over to B and up. Or somewhere in between. What's the fastest? I'll spare you. Can you see this is a shorter distance? If you added those up. If not, draw it out and measure it sometime. Or those of you that are good with trig and geometry can prove it. But it's the mid one. It takes the least amount of time. And the way it works out geometrically, let me redraw it. It's kind of like if you had an image of point B over here inside the mirror, the same distance on the other side of the mirror. And the light ray pretended like it was going straight there. But it doesn't go into the mirror. It reflects at that point and heads over exactly to that point. And what should be familiar is, if you draw a normal, a line perpendicular to the surface, then the angle of incidence is equal to the angle of reflection. It's called the law of reflection. That was true with sound waves. It's true with light waves. And that law of reflection, you can use that to understand all types of mirrors. Complicated, telescopes, curved, flat. They all abide the law of reflection. The angle of incidence has to equal the angle of reflection. But because it gets it there in the least amount of time. Make sense so far? So, let's take a mirror. Here's an object, a candle. And we're going to put a mirror here. And you know what happens when you look at a mirror, right? Where do you see yourself? Yeah, you look like you're flipped. And are you in front of the mirror or behind it? Yeah, you look like you're behind it. So in theory, an image should form over here somewhere. And if you've ever noticed, or haven't, go home and pay attention. How far behind do you look like you are? It is the same distance. And that all works out because of what I just told you. So let's see. If you take a light ray from this point, it can go in all directions. Let's take one straight at the mirror. Well, it's going to bounce right back on itself. And if you're looking over here with your big eyeball, right? Need some eyelashes. You think that light ray came from some point over here. You don't know where, but it came from that direction. Let's draw another point. What about a ray that goes up and hits the mirror at that point? Well, it will reflect according to the law of reflection. So you draw your little normal. Reflect it back out at the same angle. See, that angle and that angle are the same. And your big eyeball, not the scale, thinks it came from a point over here. Sorry, I'm a little curved there. How about one down here? Draw your normal. Angle in, angle out. Getting a pattern here. And they all seem to come from the same spot. So you see the top of the candle over there. Can you see that if we played the same game, if I took this point, and all those rays would look like they came from this point, and so on and so forth. You form an image. And this distance is the object distance, we call that, because it's how far away from the mirror it is, the object is. The image, we call it image distance. And those are the same for a plane mirror. This is a plane mirror because it's flat. It's all in the same plane. Yeah, you look the same distance behind as you are in front. And because the actual physical light rays, these guys, they don't go into the mirror. They don't go through it, I should say. They bounce back. If the image formed over here, we call it a real image, because that's where the real rays are at. But the image forms over here, so we call it a virtual image. Because it looks like it's over there, but the actual rays don't physically intersect over there. Does that make sense? Just getting you some terminology and see how this works. Now, I saw Rachel go like this. What mirrors do, and you went. A lot of people think mirrors flip the image. I want to show you how that works. Here's a plane mirror. And let's label some of these. Let's call this light ray A, B, C, D, E. Okay. If you're looking at that, your eyeball's over here. And you think to yourself, oh, A is on the right. Right? So it looks like it's on the right to you. When you reflect it in a mirror, now you have to look over here to see the light rays. And you see A comes in, follows the law of reflection, comes back right here. Hey, wait a minute. Now A's on the left, you say to yourself. Did the mirror flip the image? You can probably imply from my question, no. But what did flip? Yeah, us. We were looking this way. Now we're looking this way. We're the one that flipped. Mirrors don't flip images left to right. Nor do they flip them top to bottom. You don't see your head down there and your feet up here. Flat mirrors. But they do flip front to back. Point at yourself in a mirror. Hey, you. And which way is the image? Pointing back at you in the opposite direction. They do flip front to back. But not left to right. It is the whole point of a mirror. But it's all because of this law of reflection. And they all follow the angle in equals the angle out. That works with curved mirrors also. Here's a curved mirror. Can you see how they reflect back? But you play the same game. If you have a mirror like this, and you're standing, on this side, the light rays spread out from that point, hit the mirror, this one bounces back on itself, you draw your normal, well, I can't draw the scale, can I? And they're going to look like they all come from a certain spot back here. That's what I get when I don't draw straight lines. Oh, the heck with it. My point here, if this thing's curved, let's exaggerate. And you come in like this. You still follow the law of reflections. And you come out at a certain angle. What if this side's reflective? Same game. You come out at a certain angle. But because it's curved, it'll come back in a different way than a flat mirror or a plane mirror would do. This can do it for us, so let's just go back to it. If you're over here and you see the reflected rays coming back, they're converging to a point. We call that a focal point. Then your eyeball's over here. It looks like the rays came from somewhere out here. And you can magnify the image. It looks like it's bigger. If you flip the mirror around, now the light rays upon reflection diverge. They spread out on this side. And so if those enter your eyeball, you think it came from where? A point over here. That's the focal point. But it's a virtual focal point. It makes another virtual image. And it'll be smaller. You'll think the image is smaller. So this type of mirror is called concave, because I remember it because it's like you're going into a cave. And this kind is convex. It's curved the other way. I don't know why. All right. After class, try to end early. You have to, please, at least walk by this mirror. It's the coolest mirror I've ever seen. I'll pull it out front. It's a concave mirror. And if you're in close, you can get a really big head. You look bigger. If you get past that focal point, all those rays switch sides. Whoops. And now they can start getting, they start spreading out, and so you can look smaller when you're out here. And you're flipped upside down, too, because the rays switch side through that focal point. But the best part is right at the focal point, right about there. You can touch your finger, shake your own hand, because you're seeing a real image on this side that forms. This I look like I'm behind the mirror. Past the focal point, you get a real image formed over here. You can even poke your own eyeball out. It's kind of creepy. But you'll have to take a look at that. Here's another toy version. 2 mirrors, one on the bottom, one on the top. And there's a hole. So I've placed a little object here. You walk by, and you can see the image form up here. It's just doing reflections. So you kind of have this with an opening, a little object down here. These are curved just such with those focal points so that a light ray from here that heads off this way follows the laws of reflection and ends up doing this. And any ray that goes this way, they always go through there. So it forms the image up here, a real image. And it looks like the object's floating at the top. You can pretend to touch it. It's kind of fun. So you can walk by that one also. Funhouse mirrors, that's how they work too. You have a plane mirror, but if you curve it this way, do you look bigger or smaller? Yeah, you just pass the focal point, whether they start switching directions or not. This is called a what kind of mirror? Concave. Concave. This kind's convex. How do you look? Stretched out, maybe? You can stretch yourself out that way, too. And if you bend one way while it's bent the other, you can, that's what those funhouse mirrors do. But they all follow the laws of reflection. Make you look funny. Yeah, some mirrors in department stores. They can make you look smaller without you realizing it. So, oh, yes, I look really good. Or how about the mirrors on your side view mirror on your car? What's it say? Objects in the mirror are closer than you think. That tells me, you should at least understand at this point, it's not a plane mirror. It must be curved. Because it's making the object look a different size, and thus you think it's a different distance. But it's giving you a wider field of view, so that you can see the cars better. Where am I at? Got that. There's another type of reflection. There's two types. Specular and diffuse. Specular is what you're used to. Specular. It's off a smooth surface. That's what you're familiar with. But diffuse can happen when light reflects off an object that's not smooth, like the table. You don't see it. It's not a mirror finish. I don't see my reflection. Why is that? Because on the microscopic level, the surface isn't nice and smooth compared to the size of the wavelength of light reflecting off of it. The wavelength's big compared to it, so it just bounces right off. What if the surface is really wiggly compared to that wave? I apologize, I shouldn't have turned the lights off. Yeah, if a wave comes into here, for simplicity, let me just use beams. If one comes in like this, and this, and this, and this, and this, they follow the law of reflection at each individual point. Here, oh, that one goes back this way. Here, kind of that way. This one, down here. This one, off that way. This one, that way. And they're all kind of scattered. And it spreads out. So instead of coming right back in one spot where you can see it, specular, you see the reflection there. If you're down here, you won't see it. Not that light ray. But diffuse reflection, kind of scattered. You see it all directions, but you didn't form that image because it's scattering it. One of the simplest examples I like is a CD. That's what I'm going to do over here. There-ish. Not the shiny side, but the label side. Let's see if this works. If I take this one and reflect it off this light onto the screen, there we are. You can even read it, Office Depot. Where you can read the letters, that's specular reflection. It's crisp and clear. But where the background of the CD, the label, is kind of rough, it diffuses the light. And so that part on the reflection looks dark because it's not reflecting all the light in that direction. Here's a different CD. You can see the lines. That's where it's shiny, specular reflection. But the rough part scatters it, and it looks dark. So light reflects off almost everything, somewhat. Just some things more than others. They use that then. This can be diffuse reflection for a wavelength that's comparable to this size of bumps in the surface, right? What do you think would happen if you shone on this a really, really, really big wave compared to that? Like, say, radio waves instead of visible light? It would get less scattered, wouldn't it? Because a big wave would be less affected. That's just those big satellite dishes, or even the ones on your house. Can you see your image in one of those satellite dishes? No, they're not a mirror finish. They diffuse visible light because they're rough compared to the size of visible light's waves. But radio waves are a lot bigger. And so this looks like smooth surface to them, and it reflects just fine off of those, focuses onto the little receiver, and you get reception. They use that in astronomy a lot too, with these big satellite dishes to get radio waves from space. They don't need to be mirrored. Actually, they can be made out of wire mesh, as long as they look smooth to the size of the incoming waves. Any questions? We got one here. As he asks, I'll move the mirror in, and you can.
They're all concentrated at one certain point.
Yeah, they're concentrated, exactly. They are, well, they're like that. This concentrates all visible light, comes in, reflects off specularly, and comes to a focal point. A satellite dish doesn't reflect visible light, but it reflects radio waves the exact same way to a point. That's where the receiver is. If it didn't reflect them, it wouldn't work. That's why it doesn't work in the visible range, but it works in the radio range. Come on down and check these out and have a great weekend.